Hi everyone, welcome to my video on Street View House Numbers Dataset. Let me give you a quick roadmap of what's ahead. This presentation is divided into two main parts. Part 1, the dataset. We will explore its history, unique features, challenges, and why it's a game changer for computer vision. Think of this as getting to know the foundation before building on it. Part 2, My Journey. Here, I will walk you through how I approached this dataset from data exploration and building a convolutional neural network to augmenting the dataset and analyzing the results. By the end of this presentation, you will have a clear understanding of not just the dataset but also the practical steps to unlock its potential for real-world applications. Let's get started. SVHN dataset is a collection of real-world images of house numbers captured from Google Street View. It is developed for machine learning and object recognition algorithms with minimal preprocessing. This dataset has its roots in one of Google's most ambitious projects, Google Street View, launched in 2007 to map the world's streets and provide panoramic views. As part of this initiative, vast amounts of imagery were captured, including countless house numbers displayed on buildings. To make these images useful for machine learning, researchers at Stanford and Google collaborated to create the Street View House Numbers SVHN dataset. Released in 2011, the dataset was specifically designed to stimulate the real-world challenges of recognizing house numbers in natural environments. The dataset consists of 600,000 labeled images, in which 73,000 images are for training set and 26,000 images are in test set. There are additional set of images of 531,000 for training and testing purposes. The dataset has 10 classes, one for each digit. For example, the digit 1 is labeled as 1 and the digit 9 is labeled as 9. Interestingly, the digit 0 is given a label of 10. This unique labeling ensures each digit is distinctly identified during the training and testing processes. The dataset comes in two formats: original images with character level bounding boxes. This format consists of original, variable resolution, color house numbers images with character level bounding boxes. Example images include bounding boxes for illustration purpose only. MNIST-like 32 by 32 images centered around a single character. In this MNIST-like format, all digits have been resized to a fixed resolution of 32 by 32 pixels. The original character bounding boxes are extended in the appropriate dimension to become square windows so that resizing them to 32 by 32 pixels does not introduce aspect ratio distortions. Unlike traditional datasets like MNIST, which contains clean, handwritten digits, SVHN embraces chaos. It features blurry numbers, include overlapping digits, has tilted signs, contains shadows. First, this dataset is incredibly realistic, featuring numbers captured in natural, everyday conditions, making it a true challenge for machine learning models. With over 600,000 labeled images, it offers enough data for building and testing robust models. It's also highly detailed with character level annotations, diverse visual styles, and easy to use pre-processing steps like resizing images to 32 pixels. Plus, its detailed ground truth annotations simplify data handling for developers. SVHN dataset isn't just a tool for research, it's a benchmarking gold standard for object detection. and has numerous practical applications from postal sorting and OCR to aiding self-driving cars and accessibility tools. Best of all, it's freely available and works seamlessly with popular frameworks like TensorFlow and PyTorch. As we move into the second part of this video, let's dive into the practical side of things. What I did with the dataset. I started by exploring its structure, essentially asking questions like, what does the data look like? Are there any patterns or issues? I visualized the distribution of classes to see how balanced the dataset was. This step is important because imbalanced data can skew the results and make the model biased towards certain digits. As I explored, I also examined some sample images. These images are not just numbers on a white background. They are full of real-world challenges. Next, I moved on to pre-processing. Pre-processing is like preparing your ingredients before cooking. I cleaned the data, normalized the pixel values so they ranged between 0 and 1, and ensured everything was in the right format for the model. Normalization is critical because it makes the training process smoother, ensuring the model learns efficiently without being overwhelmed by large values. Once the dataset was ready, I got to work on building the model. I chose a convolutional neural network, which is a type of neural network designed specifically for image data. Why a CNN? Because it's incredibly good at identifying patterns like edges, shapes, and textures, exactly what we need for recognizing digits in challenging images. I designed a straightforward architecture with a few convolutional layers, max pooling layers, and dense layers at the end. Each layer plays a role. Convolutional layers detect features. Pooling layers reduce the size of the data to make computations faster, and dense layer at the end make the final prediction. After training the model, I was excited to see the results. On the test data, the model achieved a baseline accuracy of 89%. That's pretty solid for a first attempt. But I wondered, could I make it better? That's when I decided to try data augmentation to improve the model's performance and robustness. Let's talk about data augmentation. Think of it as adding some spice to your dataset. The idea is to create new, varied versions of the original images by applying transformations like rotations, shifts, flips, and brightness changes. Why do this? Because it helps the model learn to handle real-world variability. For example, a house number might appear tilted or slightly blurred, and data augmentation teaches the model to handle such changes gracefully. I applied a few augmentation, small rotations, slight shifts in position, and horizontal flips to generate a richer training set. After training the model with this augmented data, I saw improvements in its robustness and performance. The accuracy improved and the model became better at handling edge cases. Seeing the difference between predictions on original and augmented data was fascinating. To wrap things up, working with the SVHN dataset has been both challenging and rewarding. From exploring its complexities and building a solid CNN model to enhancing its performance with data augmentation. This journey showcases how AI can tackle real-world challenges. The dataset's unique features like character-level annotations and real-world variability make it an excellent resource for advancing computer vision. By taking on these challenges, we are paving the way for practical applications in postal automation, navigation, and even assistive technology. Thank you so much for joining me on this journey.